Professor Robert Fickler. Robert is experimental quantum physicist working perhaps in the interface between light, matter, and information science, if you will. He got his PhD degree from the University of Vienna. He worked with the Fickler, famous physicist, recently earned the Nobel Prize for his research. Later on, Rob moved to Canada, to the University of Ottawa, also working with very important figures in the field here. So it's really great pleasure to have him here. He's currently at Tampere University in Finland, where he started his lab, and some of the results he have been pursuing will be discussed here. And just as a note, I think the reason Robert is here today is because Rafael Barros, which is sitting here in the audience today, is a recently hired professor at the University of São Paulo, USP, Physics Institute, and he did his postdoc research under supervision of Rob. So he invited him to visit us today and give us a pleasure to hear about his recent results. So the floor is yours, Rob, and I'd like just to give a technical warning here. So this is being recorded, and that means that if you raise your arms for questions, you agree automatically to have your voice and perhaps video recorded and posted online. So if you're shy enough to not commit to that, please don't make any questions. Rob, the floor is yours. Thanks for it.
Hello everyone, thank you very much for this nice introduction. And it's a great pleasure to be here and actually talk about the research we are doing in Finland. And as was already mentioned, a lot of the stuff that I will present of the latest results was actually implemented partly or fully done by Rafael. So if you have questions, I will not have the time to go into all details, but we have the expert essentially around the corner more or less. Okay. So I'm at Tampere University, and I will today talk about, I made it rather broad, the title, that's quantum waves, because I want to talk a bit about first classical light field, then quantum light fields, and then also matter waves, all with the same idea of how we can structure them and what we want to do with them. But before we go into that, maybe you're not familiar really where Tampere is. At least I was not until I got hired here. It's fully fine. I hope you know where Finland is. So Finland is a place, or is a country very much in the north of Europe. So down here is somewhere Germany, Italy, and warmer places, but we are up here. It's a quite nice country. You see the Arctic Circle is pretty close. Rovaniemi is the place where Santa Claus lives, if you ever want to visit him. Tampere is actually in the south of the north. So it's down here. It's an old industrial town, or old for Finnish standards. So, and I always mention that they name themselves as quality, they name themselves the Manchester of Finland. Whenever I talk to UK people, they're like, why would you be the Manchester? Manchester is another good place. But I think the similarity comes from that it's an old working class city. It has a big music scene, so Finnish music scene. So it's a quite nice place to live. You see here, there's rapids in the city center. The university is a bit outside. Modern campus, depends on which building. You also get a brand new building next year, so that's good. And the university, since it's a bit outside of the city center, it's located like everything in Finland between forests and lakes. So you always have forests and lakes everywhere. You see here there's gazillions of lakes down here, so it's quite nice. But since we are pretty much in the north, you still get pretty beautiful northern lights. So as an optics person, this is something I can only encourage you to ever have the chance to visit places where you can see it, even though they usually come at 2 o'clock at night or so, and your phone tells you now. It's annoying to get out. It's a really amazing effect. This I actually took with my mobile phone like 3 weeks ago. So it happens relatively regularly. The good thing is, there's a culture in Finland that is the sauna culture, and Tampere is even called the sauna capital of the world. So why is it good? You see here, we can actually go swimming in the winter. And I always, like myself included, when I saw these pictures in the beginning, I guess you can also ask Rafael, when you see that, you're like, this is ridiculous. No normal human being does that. But then you say, well, I'm going to try once, and I encourage you to try it once because you get addicted. It's amazing. You need the warm, hot sauna afterwards. But I think it's really an amazing, I don't know why exactly, but it feels just great. Being in the hot sauna, going to the ice water, hot sauna, and so on. So it's really, it sounds, I guess, especially in this climate, it sounds completely ridiculous, but it's really something that is very enjoyable. So yeah, this is some promotion. So if you have the chance to visit the north of Europe, let me know, come by, you're always welcome. Okay, so today's talk, I mentioned already, like I want to talk about structured light, and I start with the classical version, electromagnetic fields, and what we call spatial spectral vector beams. I will explain it a bit in more detail. And then I will show you two recent results, just briefly, where we actually use these ideas of structured light fields or some of these properties and aspects in the quantum domain. So for seeing photons and photon conversions and so on. And then we also have, like, this is still the majority of the group works on optics, but we also started a couple of years ago venturing out into doing the same ideas of structuring waves, but now with meta waves. And I will show you, we don't have real results yet, but nevertheless, I think it's quite interesting because there you struggle actually quite a lot to see wave features. But it's a super interesting, at least for me, a super interesting research field. Okay, so let's start with structured light. I guess since this is an optics photonics environment, you all know the properties of light, so I can go briefly through it. Of course, light has a certain polarization, so how the electromagnetic fields on which direction it oscillates. We have linear polarization, we have also circular polarizations, and the circular polarization is connected to the spin angular momentum of light. This is known since quite a while and measured actually quite long ago. It was demonstrated. This is a video I got from a colleague at one point. I like to show because it shows that there is the light field is here, and if you trap a particle and you illuminate it with circularly polarized light only, then the particle starts to rotate around its own axis. So it's a spin angular momentum. Okay, so far so good. This is, I guess, the easy part. But there's more features of light, and one that we are especially interested in is the spatial extent of the light field in the transverse domain. So we usually work in this parallax regime. We don't focus too tight and on the light field. So then this is completely separated from polarization. So you can treat it as an individual, different degree of freedom. And it's a continuous space. X and Y coordinates, they are continuous. So what you usually do, especially towards quantum information or quantum optics, we discretize the state space. And of course, you could use pixels. But one very popular thing to discretize this state space is transverse spatial modes, and I picked one here. An example, one mode you all know is the Gaussian mode. It's the fundamental mode. You hopefully have a good laser. The laser runs on this mode. But light field can be the light fields can be more complex. This you might have also seen from laser cavities. It's the first higher order mode. We call it the Gauss mode. So here you see that the intensity now is, you have two lobes of intensity. And that's depicted here by the intensity of the color. And the color itself depicts the phase of the light field. So you have essentially these two parts of the light field, they are out of phase. That's what this color coding here means. So one is 0, let's say, and the other one is pi. So what it means, if you think about the oscillation of the electromagnetic field on the right side and the left side, they are out of phase. They oscillate like this, okay? And it's a stable light field. You can propagate over kilometers and it stays like that. It's an eigenmode of propagation, free space propagation. Okay, so this is the simplest case that I can still try to show you with the hands. There's much more complicated and interesting light fields. These are all the Gauss modes, so you have lobes, and they're all out of phase in the geometry that resembles how you find these solutions, and you have to solve the paradoxal wave Cartesian coordinates. There's another family called the Gauss modes that are, I would say, more popular for multiple reasons. One might be even that it's just like beautiful to look at because they're nice colors and you can make nice pictures. But there's actually a property, so this is the solution to paradoxal wave equation in the cylindrical coordinates. They are equally valid, they both can serve as your decomposition of the light field. It's a full set of modes, essentially. But these Gauss modes, they have an interesting property, which is the orbital angular momentum of light. And this I find interesting that it actually was just described not too long ago. Okay? In the early 90s, it was described like that and very soon afterwards verified. So now if you have a similar intensity of light field, so you see you also have this ring, just like we had earlier, but now you have this twisted phase structure. So here you have an azimuthal phase gradient or twisted phase structure. If you illuminate the particle with it, now the particle rotates around the optical axis. So it's a different angular momentum and orbital angular momentum. And we'll come back to that. Okay, this is how we, when we think about transverse structures of light, this is usually scalar structures of light. This is usually what we use, especially the Lagrange modes. Okay, and then but there's a third degree of freedom. It's a temporal domain or spectral domain, depending on how you want to look at it. And there it's similar. It's very similar. You have a continuous degree of freedom, which is time or frequency, and you discretize it. You can use time bins or frequency bins, but you can also use modes. Analog to the spatial domain, you also have here these are mid-Gauss looking like modes, so you can think of light field as a laser pulse. This is usually what you want from a good laser, just a Gaussian-shaped pulse. But you can also have two lobes that are just, again, these two lobes are out of phase. They are similar from the math. They are also used in Lie polynomials. And then you have these light fields. They're all orthogonal, different states of the light field. And similarly for spectral modes. This, I think a lot of people also work on that already in the quantum domain. We also start to look into that, to not just do spatial structuring, but also temporal spectral structuring, as you will see in a minute. But it's also actually a quite old field. People have, very often it goes by pulse shaping, because people have, of course, known that relation or the relation between frequency and time since quite a while, and then develop technique on how you can make more complicated light pulses. Very often the shape is in time. Okay, so now we have seen all degrees of freedom, but when it gets more exciting, I think, is when you combine these degrees of freedom. And one, I would say, where people look at quite extensively is you combine the spatial domain with the polarization domain. So what does it mean? You actually can think of it, or how you generate a so-called spatial vector beam. So the vector means that you now have also, you take the polarization degree of freedom in the spatial domain into account. So you superimpose a light field, let's say an orbital angular momentum light field here, that has a certain helicity and a certain circular polarization, and you superimpose that with the opposite helicity of the orbital angular momentum or this spatial structure, with the opposite handedness of the circular polarization. And if you superimpose these two light fields, what you actually get is similarly a donut looking like intensity of the light. So if you just have a camera, you see a donut. But if you then look for polarization, spatially distributed, if you measure the polarization of the light field, you see that the polarization changes across the transverse domain. So in this case, you have radially polarized light field. This, for example, is also known since quite a while that you can focus tighter than otherwise without the spatial or without this polarization structure, where you can encode other information. So it's a quite interesting thing to play around with and try to understand it a bit better for what it can be used. You see here, I depicted it in the quantum notation. So there is this Dirac notation. I will come back to that in a second. Because first, this is if you don't understand right away, I would not. If you superimpose these two light fields, why this intensity or polarization pattern comes up, you can actually make the exact same thing with the mid-Gauss modes in linear polarization. And here it's quite obvious that here you have vertical polarization on the top and bottom, and you see here you have vertical on top and bottom, and horizontal left and right side, and then in between you have all other linear polarization. So that's both are the same way how you can generate such a radially polarized light field. But let's go back to I started already saying, like, I used the quantum notation to describe such a light field. You can also do it fully classically. It's a classical light field. But many people use it by now because there's an analogy that is quite interesting. Sometimes people take it too far, but there's an analogy between such states of light and quantum states. Meaning that now, you know, or maybe you know about the concept of quantum entanglement, and here you have an analog situation. Meaning that now instead of having two particles that are entangled, here you have 2 degrees of freedom that are non-separable. So the orbital angular momentum depends on the spin essentially of the light field. So you have this non-separable state of light, and you can draw some analogy. People have used methods from quantum optics to characterize such light fields. So it's a quite interesting analogy. Sometimes it goes a bit wrong when people then think this is the exact same thing as quantum optics. It's not, it's Maxwell's equation. If you're interested, I especially highlight this latest work here by this gentleman and woman. So have a look at it. It's quite nice to where the difference come in and how you can think about it. But from an application point of view, such light fields, that's maybe one of the simplest one. You can have, for example, very complicated light fields that over propagation, if you track the polarization, you see the polarization is actually knotted or linked. So you get interesting features there. Or a relatively high field, I would say, over the last couple of years is that you can actually, if you look at such light fields and you look at the Stokes vector, or Gray vector, Stokes vector, then you see that there is a topology that is a skyrmionic topology. So people call them optical skyrmions. And you can look into the topology of the light fields. Can you make them more complex? What you can do, we also look a little bit into. Okay, so this was the spatial domain of polarization. You can do the same thing with the spectral and temporal domain of polarization. So it's the same idea. Now we have two different, let's say, spectral modes, because that's what we can do in an experiment. So you have a spectral mode with a certain polarization, and you superimpose it with another spectral mode with the opposite or orthogonal polarization. And now you have a polarization vector, a polarization ellipse that changes over the frequency spectrum. And we call it spectral vector beam. You can also have a temporal vector beam if you want. What is it good for? When we looked into that a couple of years ago, we actually thought, well, this strong correlation between frequency component and polarization is quite nice if you think you want to do spectroscopy, because you actually don't have to measure the spectrum, but you can measure just polarization. So let's say you have this light field, and you have a process that absorbs everything but one frequency component, something like a bandpass filter. And then you see that if you just measure polarization before this process, you get all possible polarization states. So if you measure just the polarization of the light field, it looks unpolarized. But after the process, you then have a very well-defined polarization. And if you know exactly this structure, you just have to measure the polarization state and you can deduce what happened to this frequency spectrum. So you can, and polarization is usually very fast and easy to measure, so you can do a spectroscopy while not measuring the spectrum. It was inspired by an earlier work where people did exactly the same with tracking of objects. So I think it's a quite nice application. Okay. Interestingly, and that's why when we got into that, it looks complicated, the light field, well, maybe at least to some extent, but it's very easy to generate in the lab. At least we realized that. So that's why we went on also more complex things, as you will see in a minute. And let me tell you how you can do it. So you have to have a femtosecond laser, hopefully Fourier limited, nice pulse shape. All you have to do is bring it into a diagonal polarization state, and then send it through a birefringent material. In our case, it was VBO. What happens is, if the VBO has the right thickness, your two polarization components, horizontal and vertical, get delayed in time by, if you do it correct, by the right amount, such that now you have a light that looks like you have a trailing and an early and a late part of the pulse, each individually different polarizations. If you now look at the spectrum of this light field, it gives you more or less this. Okay, so this is our measurements, what we did. So you can actually, you see that now you have a polarization vector that changes over the frequency spectrum. And all we did was put a VBO in. So that's quite nice. That's how we did this spectroscopy experiment. So that's, I think, a benefit. Now we'll come back to that in just the next slide. Why? Because after this, we started to think like, well, can we now we correlated frequency and polarization. We usually correlate space and polarization. Can we not combine the two? And that's what we did. The idea here is similar to before. You make a superposition between a specific spatial structure, spectral structure, polarization, and you overlay it with a different spatial structure, different spatial spectral structure, and a orthogonal polarization. So now you get a light field, and we call it spatial spectral vector beam, where every single frequency component is in such a spatial vector beam where the polarization actually changes across the transverse domain. So now for every single frequency component and every single angular position, you have a different polarization. And I think it's quite interesting that you can make light so complicated, and I can show you that it's actually quite easy to do. So that's what we want. That's what we had earlier. Just showed you that you just put a VBO in. Now, maybe you have heard about these devices. You just have to add an S-vortex plate. It's a segmented half-wave plate or a Q plate in. What it does is essentially exactly changing this linear polarization states to these two more complicated spatial vector beams. And it, again, one is early, one is late. If you now look into the spectrum, I can go forward. I can then tell you how we measured it. You will see actually that there's a huge, like a complex polarization pattern. And if you follow one line down, so here the lines, this is the angle of where you are in the beam. We did measure it with the spatial map. So if you go around the beam, essentially you see different polarizations. At least at this point here, there should be none. So that should be always circular. More or less it was okay. But at this point, at this frequency, and it was this frequency for us here in the experiment, it should be linear and it should rotate through all linear polarization. And you see that's what actually happened. So we measured it with this spatial mask that we only filtered out a certain angle. Then we put it through a polarizer or PBS and wave plates and on a spectrometer. And again, it's super simple. You just have to add 2, or if you want to count 3 optical elements. Interestingly, this light field now has all possible polarization states that exist. So that's why we called it a spatial spectral Poincare beam, because people call such light fields Poincare beams when that happens. So you span essentially with this light field, you can, wherever you look in frequency and space, you can find all polarization states that exist on the Poincare sphere. And we plotted our polarization states, and you see we even 2 times recover the full Poincare sphere. So again, it's a quite complicated light field. It was quite nice to see these connections. But actually, this was a second experiment that we did, because earlier we worked on something similar, where we then said, well, if you look into, go back to this, this description here, again, now think about quantum physics. Now we have 3 degrees of freedom that are non-separable. In translated, what's the analogous state in quantum physics or in quantum optics? It's a GHZ state. So it's 3 particles that are entangled. And that's what we want to explore, did explore actually. We had this state here. I pointed here, I would have gone back. I needed to go back. So now we have a fully non-separable beam in space, wavelengths, and polarization. So we have 3 degrees of freedom, they're all non-separable, and then you can do measurements that resemble, for example, the verification of entanglement for a GHZ state. So we did that by measuring the different degrees of freedom in combination with each other. If you're interested, this is the work where we described it in more detail. And recently, in a collaboration with Andrew Forbes' group in South Africa, we also realized that we can, by slide adjusting that, we actually have different we have, depending on which wavelengths we look at, we have different topologies in terms of the skyrmionic structures. So depending on where you are in the wavelengths domain, you have either the sign changes, or if you design it correctly, you can also have the topology changing. So you can look into making complex light fields with different topologies. Okay, so this was the classical domain. Now, hopefully, everybody knows what I mean with structured light. That's what we work on in the classical domain, but we are an experimental quantum optics group, so we usually start with this and then we want to transport it or learn something and then transport it to the quantum domain, and then I would call it structured photons, not structured light. So if you're not that familiar with single photons, well, if you have a good camera and you send single photons on a camera, they show up in one blob somewhere, here a white spot. Of course, you don't see the spatial structure right away. What you do usually is you sum up many frames, and then, for example, these are real measurements actually from my PhD times. So you see that a single photon can be in this structure. It has, of course, it has the same features. It's still light. So it has all these spatial structures. It can have also the polarization structure. So these are measurements where we show that a single photon can have also this complex polarization structure in space. So that's quite interesting. Why is it interesting? Well, if you know that a single photon can be in these states, all these modes that I described, the spatial structures, temporal structures, they are orthogonal states. It's a full basis set, so we can use it to encode quantum information. And the good thing is, with these spatial structures, we are not just we cannot just realize qubits, zeros and ones. That's what everybody usually does in quantum information. But we have a high-dimensional state space. So in this case, it's 7. We can use 7 different modes. We could use even more, and encode a higher dimensional state space. We can generate other basis states. They look a bit funky. in the spatial domain. You can do the same thing with temporal or spectral structuring. We are not necessarily doing it, but there is groups in the world doing that. Also, Rafael goes in this direction, but hopefully still sticks to its spatial structuring as well. So it's an interesting field that we are looking into. Can we then benefit from this high-dimensional state space in terms of quantum information technologies? Usually it's communication, but sometimes also sensing. So why do we think that we can benefit? Well, from an information perspective, one thing is quite obvious. If you have a high-dimensional state, you have necessarily more information per single carrier. So you have more information capacity per photon in our case. In principle, infinite. The scaling is log d, where d is the dimension. So you pretty soon you cannot. The infinite is a bit challenging to actually achieve, but you can get more information per carrier, which sometimes is already helpful. You can also use this larger state space to simplify certain quantum operations. Let's say you want to build a quantum computer and you have high-dimensional states, then certain operations are just simpler and people have shown that. Or we did simple simulations or quantum computations actually on a single photon. And then that is one thing where I really think is a strong part of this high-dimensional states, qubits we call them, is that they are more noise resilient, especially when you send them from A to B, and that's what you usually do in quantum communication and cryptography. Okay, so this is a bit more intricate to know that. So you have a bigger state space, maybe the noise, then it spreads out equally, you can think of it, but it's helpful. So this is more from the application sides, I would say. But you can do more with such high-dimensional states. You can generate nominal quantum states, for example. We investigated in one experiment a classical feature everybody knows from light fields is the Dewey phase, or as soon as you have modes, then you know about that. We investigated what does it mean on a single or multi-photon level. We called it in the quantum Dewey phase. Or, for example, again, our collaborators in South Africa showed that you have these topological features that I mentioned, fermions, non-locally. So each individual photon doesn't have the structure, but if you look at them in correlation, you can have such features. So you can play around quite nice, I think, with this more complex light fields on the single photon level. So one experiment that we did essentially fits into a line of where people, when they realize that light can have orbital angular momentum, there's natural questions appearing. For example, well, all the angular momentum should be conserved, at least that's what we believe. Then they asked the question, well, in a second harmonic generation, so in a classical nonlinear process, is the angular momentum also conserved? Very soon after this angular momentum was described first, it was 92, so 96, people did the experiment and saw, yes, in this upconversion process, two photons join to one. If each individual photon has OEN1, the upconverted photon has to have OEN2, that the overall orbital angular momentum is conserved, and they showed that. Interestingly, in a similar or also in a nonlinear optics experiment with very high harmonic generations, at first it was questions that if this process is actually conserved for good reasons, they came up with reasons, but it was resolved, so actually this process is also conserved, the angular momentum. Similarly, in the other direction, more towards quantum domain, so as spontaneous parametric downconversion, where one photon splits into two, it was also questioned in the beginning, is the angular momentum conserved? And yes, it is. It was resolved. So what people did, it's one of the seminal experiments in our field. People actually sent in photons into a nonlinear crystal, generated photon pairs, measured. This is just a way of, I will not go into the details, but this is a way of how you measure the orbital angular momentum. It's a holographic transformation. So what they saw that if the input photon that splits into two has no angular momentum, then whenever this photon here has +1 orbital angular momentum, the other one has to have -1. And they verified it also for other combinations of OEM. So, and then interestingly, this is now actually the workhorse of many experiments to generate not just entangled photon, but high-dimensionally orbital angular momentum entangled photon. And I explained it in a way that I think it's quite obvious that here you have one photon with an orbital angular momentum that splits into two, has to be conserved, like many things, like that's a typical conservation rule in physics. But interestingly, this exact experiment nobody has done. Because everybody uses a laser here, and if you know your quantum optics, a laser is not a single photon. There's a good reason. this process, this spontaneous parametric down conversion, is very inefficient. Nevertheless, we decided, let's try. Okay, so that is one experiment that we did. I will not really go into the details. So we generated heralded single photon in a first nonlinear process of SPDC. Then we sent a single photon that is heralded with its partner here. So we know that we have a single photon here. We send it into a nonlinear crystal and measure, similar to what I explained or showed earlier, with a holographic transformation with spatial light modulators and single mode fibers. We measured the orbital angular momentum of these two pairs that are generated. And I can tell you that if we send a photon in with no orbital angular momentum, a single photon with no orbital angular momentum, the orbital angular momentum is conserved. That is nice. You see a challenge here that we had in total roughly 60 events that we could detect in a measurement time of 170 hours. So it's a very challenging experiment. I think nevertheless it's just shows a very fundamental or it shows a fundamental effect. On a single photon level, we have this angular momentum conservation in these processes. We wanted to go further to also send in photons with different angular momentum. Then this was this heralding process, and the whole process was too inefficient, so we did unheralded. It slightly changes the photon statistics. It was not really an issue, as we could convince ourselves and the referees. So also for different input orbital angular momentum, the angular momentum is conserved. Then I mentioned that in this experiment, this is the typical experiment like photon in and two photons out. It's a typical experiment to generate entanglement. So, well, we had this there. We thought, well, can we actually measure entanglement? Here we have already a correlation matrix. That's good. But to verify entanglement, you also have to measure a correlation matrix in a different mutually unbiased basis. And we did that. And lo and behold, perfect correlation. All good. Now the statistics, we couldn't even convince ourselves that this is good enough statistics to claim anything. So we just put it there and put it in the supplementary and said, well, we have good reasons in the future it might be possible. We unfortunately the count rate was just too low. But this could be, you have to increase the efficiency, of course, and there's certain ways to maybe make it more stable over time and have hopefully at one point better nonlinear processes. Then you can use the scheme to herald high-dimensional entanglement, or even generate 3-photon high-dimensional entanglement, which would be quite interesting. And that was what we hope in the future one can pick up on this experiment. So this was angular momentum conservation, but you can do more with nonlinear processes. You can actually convert spin angular momentum to orbital angular momentum. There's linear processes that do that, but we wanted to do that while also changing the color of the light, of the photon, sorry. So let me guide you through it first in a classical optics setup. So let's say you have a light field that has spin angular momentum being circularly polarized, and you want to do this conversion. You have a nonlinear process to change the color, so you do a frequency conversion process. And in the process, you generate, or this light field gets, part of it at least gets converted to orbital angular momentum, such that the angular momentum overall is conserved. It turns out what you have to do is, you need this structured light field as a drive. So this is this radially polarized light field that I explained you earlier. So then this process works. And we didn't come up with this really. It was collaborators actually a bit north, east of here or so, if I'm not wrong. It was the group of Sela, Cordy, and this group. And they figured it out, that did the math in the classical domain, that this is what you have to do. So if you drive your nonlinear process with a structured light field, you can actually not just convert the light field, but also change the degree of freedom. There's still angular momentum conserved, but you change it from spin to orbit. And that's what they describe in this nice paper. Well, we decided, or actually I should give credit to Raphael, he decided, well, this is interesting, but it's even more interesting to do it in a quantum domain, because we are quantum physicists. So before we get into that, let me briefly give you an intuitive explanation what you can do here, because then you understand the quantum state transfer a bit better. So this is one way of explaining it. And another way, if you say, well, if I have linear polarization here, then I get the Samit-Gauss mode out. And here you see it even from the structure. You see that you can say this process only works if the polarization of these two are the same, right? So you see now only in the top part, they are the same. So you get this top intensity in the bottom part. Here, where they are orthogonal, this nonlinear process just doesn't work. And since we have this complicated light field, we can use any polarization. So if you have this process, you rotate your polarization, you see that the output is light field changes. Okay. Let me now go to the quantum domain. So, as I said, we set out to do it in a quantum domain. So we want to do a quantum frequency conversion process. So what we do is replace this light field here, the input, with single photons. And to make it proper quantum, not just single photons, but actually one photon out of a polarization pair. So you want to transfer the polarization degree of freedom to the spatial degree of freedom, right? That's the spin to orbit conversion. And we said, okay, let's do that for one photon, while the other one we keep in polarization. So if that works, what we expected to have is essentially the polarization entangled state turns into a entangled state where the polarization degree of freedom of one photon is entangled with the spatial mode of the other photon. And I showed you this linear polarization relate to Hermite-Gauss modes. When I did this the slide the first time, I thought this looks pretty ugly, but I was not able to do it better. So what you do nowadays as a modern person, you ask ChatGPT, and this is what ChatGPT came up with. So it looks, I have to agree, it looks better. It took me a few iterations, but yeah, now I always can put that on cover slides of my talks. Okay, good. The experiment, the concept is relatively easy. It turns out, as I guess is very often the case, the experiment is not. And here, again, I have to give credit to Rafael because he built it with also an exchange student who came from Cela's group, Andre. And I will not go into the details because it will take up too much time, but we first do we have a laser that we upconvert, then split it in two parts to use one part of the laser to generate our photon pairs. So now we have entangled polarization pairs. Then we use the other part of the laser here to structure it. And now we bring one photon and this structured light field to our spin-orbit quantum frequency conversion, this conversion process. Okay? And here it's not just a single crystal, it's actually a complex Sagnac interferometer. I will not go into the details. Again, you have an expert on that around the corner if you're more interested. But we can make this process work and quite efficiently. And then in the end, of course, to verify that it worked, we have to measure the polarization of this one photon that is not affected with the spatial mode of the other photon and see if the entanglement is still there or not. At least the theory said there should be, and we tried to verify that. So this is the state, fully polarization entanglement, just no spatial modes yet involved. This is before our conversion that we get out of this source. We get a fairly decent state fidelity, good entanglement quality and purity. If we do the conversion process, and I think that's a really a nice result, that you nearly don't see any difference. So the overlap, the fidelity to the initial state is really high, which means that the whole process is fully coherent. And let me remind you, we changed the color of the single photon and its degree of freedom, and we still have entanglement. And I think that's quite nice what you can do with nonlinear optics effects. So this is what we did. And that's already nice, but it's actually getting better because I described earlier that we have this structured light field. If I show you the picture again here, and I pointed out that there is this analogy between this light field and the quantum entangled state. So here the 2 degrees of freedom are non-separable. And if you look into this process and you look into the theory, you actually see that the final entanglement in terms of concurrence, this is our quantifier, the final entanglement that we have is not just dependent on the input entanglement, but also on the non-separability of this classical drive field. So this is the input quality of entanglement, the input state. This is the concurrence. We can also quantify the non-separability in terms of concurrence. So that's the input drive field. And both together define what is the entanglement quality or the concurrence at the output light field. And interestingly, of course, we can change this drive light field. We can make it separable or non-separable. We do that by simple polarization change. So this theta describes the angle of a waveplate that we use for that. But the measurements actually show that when we change the separability or the non-separability from non-separable to separable of this classical drive field, the entanglement quality that we measure in the end, the concurrence, actually goes down, along with changing the drive field from being non-separable to separable. And even more, here with concurrence, you never get really zero, so you cannot prove that there's no entanglement anymore, or it's hard really to do that in the lab. But you can actually use a Bell inequality test, which is a stronger criterion. And we showed that if you do the bell measurement on our converted state, we actually can control, just using this classical drive field, we can control the entanglement to such a degree that we can break this non-locality. So we now have a knob. Our classical light field can be used as a knob to control the entanglement in this conversion process. And you can make nice analogies to teleportation. So if you're interested, there's an archive paper on that. Or just ask Rafael. Okay, good. So let's, in the last few minutes, let's shift gears a little bit. There will be no complicated results because we don't have them yet. But I hope you nevertheless enjoy it. So we try to do this angular momentum only, at least in the beginning. So twist, essentially, what we do usually with light fields, twist the light field. We want to do that with freely propagating electrons and especially ions. People have done it already with electrons, but we want to go to the ions. And I can give you an example in a bit why I think that it's very interesting. So in general, you can ask, well, an ion is a particle. How do you do that? Well, I guess you all heard the wave-particle duality. When you come from the optics domain, usually you think in waves. And it's a bit weird that single blobs appear on a camera, which means that's the particular nature of light. And from the atom side, it's usually the other way around. You think of it as little balls flying around, but then they also have wave features, and that's exactly what we want to explore. So the challenge is now to make that, essentially, to have a fully is not possible, but to have a coherent beam of electrons or ions. In this idea that you have just quantum objects and you structure them. So what you can say, well, the first time it was verified, I showed you earlier this experiment in 2001, where they showed entanglement of photons with angular momentum. So this, you can say, this was the starting point of this quantum objects with angular momentum in freely propagating beams. Then with electrons, 10 years later, it was first described, it was 2009, it was first theoretically described, but experimentally verified in 2010. Then, a couple of years later, it was actually shown for neutrons. I think this is a bit, the claim was too much, so this is the better experiment where they finally verified it. You can also have a neutron beam that has orbital angular momentum. And then also in the early 20s, people have done actually atoms and molecules. So this is now all covered, but people explored. But we want to go, so we want to do also a bit electrons, but we want to go in this domain, essentially, saying that we have now heavy particles and they are charged. So why is it interesting that they are charged? Because this is also heavy particles, but they're neutral. The charge actually, because you have this orbital angular momentum, and since you have a charge, you have an azimuthal current density in the beam, which means you can think of it simplified as a current that goes around like this. And if you know your electrodynamics, a current like this leads to a magnetic moment in this direction. So these it has been verified for electrons, of course they are also charged. So it has been verified that there's an additional magnetic moment that you only have because you have this orbital angular momentum in the electron beam. And we want to explore that, especially for ions. Why? Because if you know a bit of your quantum, or you remember a bit of your atom physics courses, there's an internal level structure of atoms. They are susceptible to magnetic fields. It's a Zeeman effect. And we want to explore if this ion being in this twisted wave structure have an effect on its own level structure. So we're working currently on the theory, and we are building the experiment to explore this domain. It's I think a quite interesting, very interesting, I would say, physics question. If you ask me for applications, I have none. I think it's beautiful as it is. And luckily, there are some funding agencies in Europe that also agree that this is worthwhile, nevertheless, spending quite a bit of money and time. Okay, good. So how we do it? Quickly run you through. So you need a coherent beam. We don't have lasers for electrons or ions. So what you do is we use an old trick from optics that relies on the van Zitter-Zernike theorem, meaning you start with a point-like source and you just let it propagate. If you look at how big this coherence area is that you get, it scales not very favorably with wavelengths, and electrons and ions have very, very, very short wavelengths. So it's a bit challenging. What we do is we start with, at least in the beginning, we start with a nanometer-sized tungsten tip that we etch ourselves, and you can just put there a high electric field, and the electrons get sucked out only off the tip, or you bring atoms close, and then the atoms get ionized, and you accelerate them. So this is our result. This is how it looks when we have the vacuum chamber open, and inside there you not really see it because it's covered with electrodes, the extraction electrodes. We have this etched nanotip that we are currently at 10 nanometer, and we already have developed processes to actually, in the chamber, grow here even a single atom tip to have the tiniest possible source, point-like source that we can imagine. Because if you put in the numbers after 1.5 meters propagation, for ions, you only get a few tenths of microns of coherence. So that's why we have our chamber being 1.5 meters long. You need ultra-high vacuum to shield it from the environment. We will have a magnetic shield. Of course, it's the vacuum chamber. It's electrically shielded. This is the whole system, how it's now actually standing like this in the lab. But of course, we have it designed everything. We made it in the computer so you can make nice pictures. This is a picture of our electron beam. In the end, we will have time resolution as well with a time fixed camera. So we think about already how we can benefit from that. So the question is now, how do you twist, how do you make the structure? And the good thing is with charged particles, there's optics for that. Or even in this case, you can just have electrostatic fields and you can imprint this twist. Of course, this benefit comes with a downside because charged particles interact with everything like electrostatic stray fields or electrodynamic stray fields even. So we have to shield properly. But the good thing, what we benefit is from this interaction of the charge or due to the charge with electrostatic fields. And people have showed it already for electrons. So if you have 2 nano-sized or very small needles and you put opposite potential on it, then you get an electric field distribution that pretty much looks like this twist that you want to imprint. And if an electron or an ion propagates through, it accumulates a phase according to this potential. So we exactly twist with this. We have a colleague in Helsinki, so a bit more south of Tampere, that makes the nanofab. This was the very first promising result, and we only had to etch from the back that we have our hole, and of course everything went haywire. So we don't have any chips yet, but we hope that in the next months we get our devices that we can test, that we can actually structure our electrons and hopefully ions. It might take a bit longer with the ions, but we are getting there. Final thing is how you verify that. There we again rely on our optics expertise. So you can verify orbital angular momentum by just looking at how the structure changes if you send it through a cylindrical lens. And you can easily do that also for electrons. It has been shown this is actually electron pictures. So if you have this orbital angular momentum in the focus after cylindrical lenses, you get this kind of Hermite-Gauss mode looking like structure, rotated depending on the sign, and the lobes depend on the orbital angular momentum. By just looking at this image, you can measure essentially, or you know what the angular momentum has to have been beforehand. Okay, so with this, I'm at the end. I hope I showed you that you can do, in actually surprisingly sometimes simple setups, quite complicated light fields, and play around with that. At least that's what we're going to do. And now we'll try to bring that, look into topological features or bring them to a quantum domain. For example, we look now how can we do that for entangled photon pairs and what does it mean there. But I also showed you that we are already doing quantum optics experiments, and they're fundamental experiments to verify angular momentum conservation in nonlinear processes, or use conversion of nonlinear process to, even in a controlled way, transfer not just the frequency of a photon, but also the degree of freedom. So we transfer spin to orbit. And we are working towards quantum matter waves, they're intrinsically quantum, and hope if I'm coming back here in a bit, I can have results on that and I can show you. With this, of course, I have to, it's very, very, very rarely me going to the lab. So there's, this is the group, the current group in Tampere. But actually the people that did the experiments that I presented is mostly these two, a former PhD of mine, and of course, Rafael, who's now here in Sao Paulo. And especially the spin-organ conversion experiment was a collaboration with Zela, and Andre visited us, and they worked together on the experiment. For the matter wave experiment, it was we have a theory collaborator in Germany and our nanofab person at Aalto University, which is near Helsinki. And with this, thank you for your attention. Thank you very much. Questions? Question? criticisms, always do.
Yeah, thanks for this great talk. So, I'll stick to the last part, just not to take the whole time for the questions, but you might be aware of the recent work by a group of the methodologies, where they're doing this like crunch point, they call it, was a piece of paper that came out of Nature. They're building waveguides for diving charged particles. And I seen a part of this talk. I got late into the talk, so I didn't get a full detail, but I recall a picture where the particles are spiraling for a given electrostatic field distribution. I got it right, you don't tap into angular momentum, but the very nature of the motion seems to have a very strong connection with orbital angular momentum. I think what the net result is that they can guide this particle for much longer distances, perhaps achieve your scenario larger coherences. And did you look into this? Is there a connection? Maybe my question is, if you are aware of this work, is there a connection to this idea of imprinting angular momentum into charged particles, or these are different?
I think I think I saw the paper, but I didn't read it or even like scanned it. I saw the paper, so I have to be careful. The way you describe it now, there's definitely a connection because I would say what you describe is more classical because you have a particle that actually rotates. In our case, we have a particle that is smeared out and has this phase distribution. And because of this, we actually have a current density that goes in the azimuthal direction, which is a quantum current density if you want. So it's really a wave. The ion is, I mean, there may be different ways of how you interpret coherence, but I would say from my perspective with quantum domain, if you have a transverse coherence, the particle is not defined anywhere. It's just everywhere, and the density distribution is given by the density distribution tells you the probability. So I think there might be a difference, but since there is this connection, I'm pretty sure you can make relations, but the way you explain it, it sounds a bit more like classical analog. Could be. I have to look at it. I didn't. Yeah, I have to look at it. Very, very good question. Thanks.
When you have this quantum currents, can you predict the magnitude of the magnitude?
Yes, it is quantized because you have a quantized number of orbital angular momentum, and then it should be also a quantized current that you have there. And what we actually want to explore, but our collaborator on that, even and an author of the paper that predicted this theoretically, is not convinced anymore that it actually works. I don't buy it yet. But if you send this twisted charged particle in this state through a conductive loop, then you induce a current, just like you move a magnet into a loop, a conductive loop. And this then also gives, from the current, you should be able to measure what orbital angular momentum, how strong this twist is, or how fast this current is, or you want to see it. This is what we want to explore if we can actually see such an effect. People should see that with electrons, they didn't, because all the experiments use electron microscopes. So if you want to have a twisted electron beam, and you have enough money, just buy a TEM. Nowadays they are coherent enough because they use point sources, because they're very bright, and you can do such experiments. The downside is you are very limited because it's a commercial system. We hope we can do more with our home built system that is crappy in terms of imaging, but hopefully good for fundamental physics. So yes, there is a connection to the current, or at least that's what theory predicts. And people use very large orbital angular momentum to measure actually when they pass by magnetic needles, to measure the effect that there is this magnetic interaction. So this has been verified, or rotations in a magnetic field or electric field with electrons.
You said in the when you have this photon complex states, they are better for quantum application or other applications because they are more resilient to noise. And
my intuition is that should be the opposite, because more complex states with higher dimensions are more sensitive to all kind of noise. What is that?
Yeah, it's good. It's maybe a bit counterintuitive when it comes to this noise resilience. So you could think it's also not. Yeah, when you look into the details, it's not as easy as I phrased it. But the thing is, you can think of it that you have for a certain, in space or in time, you have a certain noise level. So now, if you discretize it just to make a qubit, like in the camera, you just use 2 pixels, then you have per pixel quite a lot of noise. But if you now discretize it to many states, then you essentially smear out the noise over this bigger state space. So that's one way of seeing it. We did a work where we showed that you can do this entanglement distribution nearly by daylight conditions, and that was one way where we showed it. Another way is also that with these high-dimensional states, you have more mutually unbiased spaces. So if you want to characterize your state, you can do more measurements and therefore have a bit more noise resilience. The first that I explained is much more valuable, it works better. But nevertheless, this is the benefits that you have. That being said, if you generate these high-dimensional states and if you transmit them and measure them, usually or sometimes you actually introduce more errors because polarization you can handle nearly perfect. And spatial modes or temporal modes is actually challenging. So the technology is not there yet. That, from my experience, usually you go to 2 dimension is good, 3 dimension is better, 4 dimension is even better, 5 dimension is already worse. So, but it depends strongly on the actual implementation. But the idea is, the way I see it is really that the noise, the same noise you have for a given area or time, you smear out over many more states. And therefore it doesn't matter that much. Hopefully it's about quantum frequency conversion.
It's not a frequency conversion. But you mentioned that maybe you can observe the Zeeman effect.
That's the main idea.
When you have the OEM imprinted on the ions, right? But my question is that when you have an OEM, the probability that the ion will be at the center is very low, right? You have some kind of ring structure. And wouldn't the magnetic field be right at the center? So there would be magnetic field where there is no ion.
Well, it has this. It should have an effect also off center, but then of course the probability is 0 at the center. So maybe there is where it will be the strongest. But we are looking into the theory. I mean, there's even different proposals where you can then make more complicated structures and see an effect. This is for me the most intuitive one, but there's no theory on that. I can just come up with this hand-wavy argument that I mean, it might be to find a trade-off to where to go, where to measure then exactly. Maybe you have to block certain parts of the beam to see the effect stronger, but have lower signals. So it might be a trade-off. But it should be also influencing in other parts, right? It might be the strongest.
Maybe a related but very naive question. Would there be a difference with the sign of the wave? Like if you have clockwise or counterclockwise rotating wave, would that change something in the energy levels structure somehow? Maybe that's also.
That's the hope, because you try to. It's some kind of like, I don't know. Or a different way of looking at it, it's a spin orbit, but orbit in the spatial monitor, you have the spin of the electrons. So this is a spin orbit effect, and then I would say you see a different shift. Yeah. So at one point I did a back of the envelope estimate, and it was really small. I don't trust these calculations really, so we now do it proper. The beauty there is with this that I can give you the number that I came up with was like 6 orders of magnitude smaller than this hyperfine thing, the actual spin orbit effect in atom. And that sounds really bad, but you can actually do here, you can switch the effect on and off, right? We can imprint OEM and not, and so on. And there we hope we can do with lock-in amplification techniques in K. But we go in this direction because we have other ideas to do with the ions. But if we figure out the theory that there should be an effect, I hope, if it's not minus 50 or 10 to the minus 50, I hope we can measure it. But it should be the opposite, it should split, I would say.
Any more questions?
I'll follow up on that actually. So you expect then to see the orbital under momentum, or actually the hyperfine structure there. So then you have to probe optically your ion. So then you have, so just so I understand the setup there.
Yes.
So you do have a sort of like an SEM, but you need to see the ions there with your cylindrical lens, so you can actually see that it's imprinted. And after that, you want to shine like a laser or something, and then to see the hyperfine structure. So that's the rough idea that you want to do.
But the seeing is not necessarily, or it's not necessary later on. It's just the first verification that we actually have a coherent beam and we imprint orbital angular momentum. But then we don't need it anymore, or when we know that okay, the setup is working, then we don't. Maybe depends how the setup will be at that stage if we can still record it. But we then want to do essentially spectroscopy on the ions that are in the beams and see the effect absorption vectoring. So the first, this is the idea. We do spectroscopy, but of course, the effect is very small. It will be challenged to have the right lasers. And helium is really bad. People have done spectroscopy. I just recently saw that, but the laser wavelength is, I think, 100 something nanometer or something. So not so good. We want to go to beryllium, which is not much heavier. So it doesn't get even more complicated. But there's laser sources that are in a decent range. I think 266 or so, and people have used it for ion trapping. So there we know the spectrum, and we know the level structure perfectly well for beryllium. So this is the idea that once we can structure ions, we can. I just wanted to mention it because I think this was the main reason why I got super interested in this, and even I think was to convince the funding agency.
Any last question? If not, let's thanks for that again.